All right. Recall from one of our last sections that one limitation of the Friedel-Crafts alkylation is the potential for carbocation rearrangements, unless, of course, we want it to rearrange. Now, propylbenzene cannot be synthesized directly from a good yield by a Friedel-Crafts alkylation because rearrangement of the cationic intermediate leads to 1-methylbenzene instead. And so we saw that previously. So there's a workaround for this. So to avoid that problem, we can use a Friedel-Crafts acylation instead, where we form the CC bond to the aromatic ring without competing carbocation rearrangements. Because the intermediate product of an acylation reaction is an aromatic ketone, right? The carbonyl group then can be reduced to an alkyl benzene. And one example here is using the Clemenson reduction, which we talked about in section 20.4. Okay, so you can still use these, but what this does is it avoids a carbocation rearrangement that we don't want. Okay, and so there's some organic synthesis considerations that we need to think about. So let's do an example. Show how you would synthesize this compound using benzene as the only aromatic starting material. So when we look at this, the first thing that I think of initially out of the gate is, okay, I want to attach something to benzene, right? And so I'm going to generally cut it right here. Obviously, we're going to have a carbon-carbon forming reaction. And our go-to a lot of times in this is, hey, what if we could use an alkylation? Because that's a large alkyl group. The problem is if we do this, a primary carbocation would be produced, and that's going to rearrange to a secondary carbocation, right? So if we undo this, then the part that's undone would look like that, okay? And so that would immediately rearrange to the secondary carbocation. So instead of doing that, what if when we go through and undo this, right, where we undo this right here, we undo a carbonyl reduction first, right? And then we go through and undo the Friedel-Crafts acylation. And I just keep needing more space, so hold with me as I maybe. Apparently this is just going to fight with me today. Nope. So we're going to leave it there. So if we were going to write this now in the forward direction, we would come here and we would say, all right, I'm starting with benzene. That's kind of a terrible bond, so let me make that a little better. Okay, and then we're going to add that. And then we're going to go through the Clemenson reduction. Well, there, finally it's doing what I want it to. And there you go. So that's a really good example of a synthetic workaround that's really helpful. The next section also talks about some organic synthesis as well. And so here are common reactions that generally are used along with aromatic substitution reactions. So basically, these electrophilic aromatic substitution reactions really allow us to incorporate a variety of substituents onto an aromatic ring. But unfortunately, several substituents cannot be put in place directly by electrophilic aromatic substitution, kind of like we just saw, right? So we're going to discuss how different electrophilic aromatic substitution reactions can be used to incorporate a substituent that's different, that can subsequently be transformed into the desired substituent, okay? So, for example, let's say you needed to incorporate a carboxylic acid group onto a ring, okay? We didn't see any of those, that the ability to do that in the 5 reactions that we looked at. So what we see here is that you can brominate the ring first, right, which results in bromobenzene, which then can be treated with magnesium to produce a Grignard reagent. And then the Grignard reagent can be reacted with carbon dioxide gas, and then what we'll see here is that reaction will produce a carboxylate anion, which is then protonated in the acid workup, right? And then that's how you can add CO2. That's how you can add the carboxylic acid group onto the benzene ring. So it's a combination of many different syntheses, okay? Now, there's a lot of alternative ways to incorporate carboxylic acid groups, and you can begin with a variety of monosubstituted benzenes where the carbon atom from the substituent is directly bonded to the ring, which you can see here. Oxidation of substituted benzenes using potassium permanganate, which is KMnO4. So I just want to remind you that this is potassium permanganate. It's a really deep purple complex. You can heat it in a basic solution, and it's going to produce benzoic acid after an acid workup. And several of these precursors can be produced from a Friedel-Crafts reaction. Now, here's the deal. Permanganate oxidation reactions are believed to proceed through radical intermediates. The carbon atom is bonded directly to the phenyl ring, would be known as a benzylic carbon, and it's particularly reactive under these conditions. And so that's basically why the product of each reaction is the same, independent of the group that's attached to the benzylic carbon, which is the carbon that's right here, right? So, but there's some limitations to this. The permanganate oxidation fails when the benzylic carbon is quaternary. And that means that when that benzylic carbon, which is the one that's attached here, right, that benzylic carbon is bonded to 4 other carbon atoms. So this is not oxidized through to benzoic acid. So when a substituent on a phenyl ring is attached by a carbon atom, that potassium permanganate oxidation requires the benzylic carbon, which is attached here, to be bonded to at least one hydrogen atom or be part of a pi bond. Okay, so the benzylic carbon must be bonded to at least one hydrogen atom or be part of a pi bond. So in the synthesis, the CO2H group might not appear in the target molecule. Instead, the CO2H group can be transformed into other functional groups like esters. And so I'm sure the burning question in your heart is, ooh, Dr. Pierce, can we see an example of that? And my answer would be yes. Let's look at that. So let's propose a synthesis of ethyl benzoate from benzene and any other compounds containing 2 or fewer carbon atoms. Okay, so when we sit down to look at this, I kind of always do my my normal thought process, which is to say, all right, I've got to start with a benzene. And so that means I've got to figure out a way to put this group onto the benzene. Now, one of the things to be aware of is I also look at functional groups. And so I look here and I say, look, that's an ester, okay? And so the question, of course, becomes, well, how can an ester be synthesized from a precursor with fewer carbons? And I remember way back in chapter 23 that we learned that an ester can be synthesized from a carboxylic acid and an alcohol. And so what I would do is say, all right, hey, look, let's think about this in reverse. Well, let me make a decent benzene ring there. I've only been drawing these benzene rings for 20 years, right? And so let's undo that chapter 23 esterification. Right? And so now I could put my carboxylic acid here. That's that carboxylic acid group. And then react it with ethanol here, right? And that would give me 2 or fewer carbon atoms. Okay, so that checks that box for this question. So then the question becomes, well, then, so that one box is checked, but now we need to get this back to benzene, which is the other box. So how do we do that? So we can take that molecule, and if we think backwards, right? Maybe I say, look, I want to undo an oxidation. Okay. And so I'm going to start with this guy here. Okay. And then from that, I can undo an acylation. Now, here's the thing, right? Benzoic acid can be made by oxidizing one of the types of compounds that we talked about in the previous slide. I can't go back because it'll make the screencast break up. But here are a few things to kind of be aware of. I just arbitrarily kind of chose this. If you wanted to choose a different one, you could. Okay, so I'm going to undo an acylation, right? But you could also undo an alkylation if you wanted to. Okay, so now we are maybe going to draw this in the forward direction with all the reagents. So we take the benzene and we are going to do an acylation reaction. And there's our carboxylic acid side chain. And then there's our alcohol and our H2SO4. And now there's that molecule. And so this is how we can incorporate the oxidation reaction into a synthesis. Let's look at some more examples. So an amino group is typically not incorporated into a benzene ring directly by electrophilic aromatic substitution. So that would be this group here or this group here. Instead, the benzene ring is often nitrated first here, followed by the reduction of the nitrate group to an NH2 group. That reduction can be carried out either using catalytic hydrogenation here or by treatment of a metal like iron. Sometimes, so there's iron used here, but sometimes tin is used under acidic conditions, followed by sodium hydroxide to neutralize the acid. All right, and so you can see, maybe, if this pen, there we go. You can see the sodium hydroxide there. Reduction with a metal under acidic conditions resembles the Clemmensen reduction in chapter 20, where the carbonyl group of a ketone or aldehyde is reduced to a methylene group by treatment with that zinc mercury amalgam in HCl. The reduction of the nitro substituent to an amino group should be considered if the target is an aromatic ring, okay? So only if we're looking for an aromatic ring. And especially the aromatic amine could be used as a synthetic intermediate towards the synthesis of a different target. So we can see kind of both of those. Now, all right, bromobenzene, right here. All right, if that broke up there, I just replaced a part on my Apple Pencil, so I'm hoping that helps me a little bit more with being able to point and drag and those types of things. So we were talking about different reactions that you can do with benzene rings, basically. And so you can produce bromobenzene here, right, when aniline, which is this molecule here, is treated with sodium nitrite under acidic conditions, followed by copper 1 bromide. Now, when we look at this, right, this is a benzene diazonium ion formation reaction. And so what happens here is in this mechanism, you get a proton transfer. With hydrobromic acid. Then you form nitrous acid. And that undergoes a proton transfer. Oop, I forgot my electrons there, where that goes in there, and those electrons go on bromine, right? And then that ends up with a protonated water, and that, of course, is an excellent leaving group, so that jumps right on off there. And that undergoes heterolysis. Okay, now when that undergoes heterolysis, what we're going to see here is this oxygen double bonded to the nitrogen with a positive charge. But we have a resonance structure here. And I'm going to draw the resonance structure because it's the resonance structure that works best as we show this mechanism. And so the resonance structure that we see is this one here. Okay, where there's a positive charge on that oxygen. And so it's that resonance structure that, remember, both, when we talk about this and show these in mechanisms, remember that we have neither this one nor this one. It's a hybrid here. But when we show mechanisms, it's easier to show a mechanism with one versus the other. So now this goes through nucleophilic addition, right? Where these electrons come onto that nitrogen and those electrons go on the oxygen. And so in that case, we formed a nitrogen-nitrogen bond, and there's a positive charge there on that nitrogen. Now, we're going to undergo a proton transfer. With water, where these electrons come out and they're going to grab a proton, okay, and then these electrons go back on the nitrogen. Now, once they undergo proton transfer, this guy will go on and react again with water. And I said water real confidently. I meant a hydronium ion. Where we go here, and then those electrons go there. Now, this is a particularly long mechanism. So I have given you 2 pages to do this, but I am just going to keep on rocking down this particular slide. So if you need that second page, that's fine. So what happens here, right, is that, I'm going to move my arrow here and call this a proton transfer. Well, it is a proton transfer, but I'm moving my arrow here. Is that again, so I'm drawing the brackets. We are going to get some resonance structures here. Okay, and so there's this resonance structure. Now, what I'm going to do is show you the resonance structure arrows in a different color. So these electrons go here, and then these electrons go up on the oxygen. And so that gives us the resonance structure where that's going to go through and react now. Because it's easier to show the mechanism with this particular one. But we remember that both of these are in, it's really the resonance hybrid that reacts, right? And so when we look at this, I don't know why we're doing this now. There we go. So, okay. So when we look at this, okay, then what's going to happen is another proton transfer. With water. And so what happens here is this comes in and it grabs that proton, and then those electrons go on the nitrogen. Now, once it does that, right, it's going to go through an additional proton transfer reaction. where these electrons come in and they grab that proton, and then these electrons go on the oxygen, and that gives us this guy. Which then will go through a nucleophilic elimination. And remember, water is such a good leaving group. And so that leaves us with a benzene diazonium ion, okay? Now, this possesses the N2 plus group, which can behave as an excellent leaving group and depart as N2. So the ion is highly reactive and must be kept at approximately 10 degrees Celsius or below to prevent decomposition or explosion. Okay, now, why would we go through all of this to get this ion? It makes it possible to carry out subsequent substitution reactions simply by choosing the appropriate nucleophile. So look at all of that this can here, right? So this is the Sandmeyer reaction, right? Here, okay, these require a copper catalyst, but there are other substitution reactions here, and we can make all of these compounds just from this guy here, right, which is pretty cool. Let's talk about the Sandmeyer reactions really quick. These are named after the Swiss chemist Traugott Sandmeyer, shown here. So even though the reactions in equation 2438 involve nucleophiles and excellent leaving groups, they do not universally proceed by ionic nucleophilic substitution mechanisms. Some of them resemble SN1 mechanisms, and others are believed to involve radical intermediates. And remember, those intermediates contain unpaired electrons. Now, some of these can also be produced by electrophilic aromatic substitution reactions we've seen here. So, for example, the bromobenzene shown here and the chlorobenzene can be produced through those halogenation reactions. However, the benzene diazo ion intermediate provides a lot more flexibility in synthesis, and it allows us to synthesize compounds that cannot be synthesized directly by electrophilic aromatic substitution. For example, remember that iodination and fluoration of benzene do proceed by electrophilic aromatic substitution, but sometimes there are issues, right? So if we begin with the arene diazonium ion, iodobenzene and fluorobenzene can be synthesized in a rather straightforward manner. Similarly, the benzonitrile and the phenol, which is here, right, cannot be produced directly from benzene by electrophilic aromatic substitution, but they can be produced by incorporating the benzene diazonium ion as a synthetic intermediate, okay? And so this gives us a lot more flexibility. Let's do an example here. So, show how to synthesize benzene nitrile from benzene. When we do this, right, I always like, particularly with benzenes, I come in, I'm like, okay, great. We got to attach something to benzene there. So it's got to be that guy. So how do we go through and do this? Well, we are going to, the first step is to undo a Sandmeyer reaction, right? And then we are going to undo, and this is what this is called, a diazotization reaction. And that gives us this amine here. And then we're going to just undo a reduction. And then once we undo that reduction, we've got our friendly NO2. Oh, that's a terrible bond here. And then once we undo that, we now just undo a nitration. And we're left here at our benzene. Yay! So let's look at this in the forward direction then, and put all our reagents in. And so when we go through and put all our reagents in, we go through a nitration. We are going to add HNO3, and then we want to speed it up, so we're going to add the H2SO4. Then we are going to add hydrochloric acid and iron and sodium hydroxide. And that gives us the amine. And then we are going to add NO here, H2SO4. And then we are going to finish the synthesis using a Sandmeyer reaction, which is a CuCN, and get this guy. And there we go. We are done. So this concludes chapter 24 for us. We are going to jump into chapter 25, which is aromatic substitution 2, and we're going to look at reactions of substituted benzenes. So in the next chapter, we're going to say, hey, look, when we already have a group attached here, what reaction will that one go through? And so that's our next screencast.